Here is a typical power supply similar to those we've seen from Statoil platforms so far. I'd like to pass you over to crucial members of my team to show and discuss how we go about the repairs.
I'm Lisa Rowe, the production manager of the electronics department. Upon receipt of a repair, my job is to allocate the unit to an engineer for initial diagnostics and repair.
Okay, I'm going to find out how we're going to tackle this repair. Let's find out what it is first. So, 24 volt, 12 amp power supply. Standard IEC power, standard power connections. So this will go under one of our standard test procedures. What we would do with this is we'd assess it to find out what the faults are with it first. We put those faults right, and then we carry out a standard overhaul to improve the reliability of the power supply, and then we do a full test to prove its performance to its specifications, which are clearly marked on the case on this one.
Jeff, you've got the power supply here with what looks like the covers removed. Can you tell me what we're going to do now?
Yes, what we've actually already done is we've powered this up and found it actually didn't power up at all. There was no output, it was apparently dead. The first thing we do is actually do a visual inspection, looking for any obviously burnt components. And there's a transformer here, it looks like it's got burnt windings. We also identify what we're going to change in our standard overhaul. That's anything that can affect the reliability of the power supply after we've carried out the repair. Such things as relays, the electric capacitors, which age of time and temperature, high temperature and high ripple currents on them actually shortens the lifetime of those quite considerably to about 3 or 4 years sometimes. Opto-isolators, these degenerate with time, they lose their sensitivity as time goes by, so we find we have to replace those. And we look at the power resistors here for any obvious signs of burning, which means they may be likely to fail soon. Capacitors like this, looking for cracking in the cases, which could allow moisture in and cause them to fail. And then we look at the solder joints on the board to make sure the joints are good, particularly on large heavy components like transformers, where we're looking for cracking of the joint, like a little circular crack around the wire, which will cause an open circuit and cause a future failure.
So what I get from that is we're not just carrying out a repair of a board, we're fully refurbishing it for any components that will wear, that we are able to give a guarantee on this board for the customer. Is that correct?
Yes. We're trying to make sure that after the repair is done, there's nothing in here that's going to cause a failure within the next few years. When we powered this power supply up, there was no output. Diagnostic tests we did show that the reason for that was the failure of this pulse transformer here, which is part of the gate drive circuit for the chopper for the primary side switching of the power supply. So what we need to do is remove this transformer and replace it with a new good one. Okay, we need to replace the faulty transformer. Now the faulty transformer is on what we call a hybrid. A hybrid is a circuit tile like this. It's made of a ceramic substrate and all the surface mount components are bonded to it. They're very fragile and they absorb a lot of heat, so they're difficult to replace components on. So we have some special techniques that we've developed to be able to repair these successfully. Now I've removed the tile from the board and mounted it in this frame because of its fragility. We don't want to bend it, we don't want to cause thermal stress or break the connections. So what we're going to do is remove the transformer. We have a special tool on the hot air gun that allows us just to heat up the legs of the transformer without affecting any of the surface mount components in its vicinity.
Yeah.
Okay, so we're going to remove the transformer. I've got the temperature set for the correct temperature for the lead-free solder that's used on this. And it's just really a matter of warming up the legs and waiting for the transformer to move. It tells me it's free of the board. So it's just about ready to come free. A bit more heat, and we'll pull the transformer free and left the pads intact. Okay, we're now going to prepare the pads to have the new transformer fitted. So all the old solder needs to be removed very carefully so that we don't destroy the pads on the hybrid. Okay, we have the new transformer which is going to fit. Now, obviously, we're going to make sure we have the correct orientation. So the markings on the transformer showing where pin 1 is. And we're going to solder that back onto the board. The technique is to secure one leg initially, place the position correctly, and then solder the remaining legs to the pre-prepared tracks. And once the soldering is done, we'll then inspect the joints under the microscope to make sure they're good.
Hi again, Jeff. I see we're at our microscope inspection bench looking at the hybrid tile that you've just replaced the transformer on. Can you tell me what you're looking for now, please?
Yes, the flux has been cleaned off the solder joints, and we're checking that the solder joints are good. There are no shorts or breaks. So we're just looking at the joints, and what we're looking for is a nice profile of the solder on the lead out leg. Those. The joints look nice and shiny, so they're not dry joints. There are no breaks, there are no solder whiskers or shorts. Let's have a look at the other side. Again.
So are you happy now that we've carried out the successful replacement to that transformer?
Yes. We'll again put this back in the board and test the power supply once more, and the fault should now be cleared.
Thank you, Jeff.
Okay, we've repaired the hybrid tile. Before we fully reassemble the power supply to test it, we're going to do the overhaul work. And part of the overhaul work is removing the electric capacitors and replacing them. And we're going to replace them with new capacitors, 105 degrees C temperature rating. Most electronics is built with 85 degrees C rated capacitors, and we improve reliability by fitting 105 degrees C rated parts. So we're going to unsolder the capacitor which we've previously marked red. We'll unsolder it and pull it free. You can actually see this is actually failed. There's a goo actually come out of the capacitor which we need to clean off before we fit the new one. Okay, there's a break there, so I need to get. We've removed the faulty capacitor, and you could see the electrolyte had leaked out of it and left a stain under the board. We've cleaned that away. We're now going to fit the new one. Obviously make sure that the polarity is correct. Fit it into position. Mechanically crimp the legs over to hold. Cut the wire to the correct length. Then resolder. We need to make sure the solder flows correctly through. To the other side. And we make sure the component is in correctly and is firm. Okay, the first capacitor's been replaced. We removed it. You can see the electrolyte leakage on the base. We're now going to mark it that we've replaced that one. We're then going to go on to replace the remaining capacitors. They'll all be different values. The opto-isolators, the relays, and we're going to check the thermal contact of the power devices. One problem we know of is these clips can crack or lose tension, and that one's a bit loose. And also the thermal conductive pad underneath can puncture, and that causes insulation failure, and that will cause the power supply to fail. So these will be removed, checked, and put back into position and replaced where required. We've now replaced the electrolytic capacitors. You see now marked with a green dot, and also the opto-isolators and relays, and the hybrid towers being refitted. So we're ready now to inspect the solder joints on the underside to make sure they're good, and then finally assemble the power supply for testing.
I see that we're back at the microscope inspection bench and you're checking the solder joints on this power supply. Are you happy that all the joints are okay and we've now basically finished the repair on this?
Well, let's have a look at the joints. Not happy. There is one here, you see a little ring around the lead out leg. That could be indicative of a crack in the joint. We would have to rework that joint and inspect again.
So does this carry out on all the joints on the back of this board?
Yes, we carry out this check on all the joints. When we're happy with them all, the job is ready.
Yeah. And I see that's not one we've reworked, that's one that has over time, I take it, cracked or...
Yes, that is an original manufacturer's joint. The usual causes of this are either heat stress, expansion and contraction of component fractures the joint, or can be a chemical corrosion effect that can cause a joint, but could have just been poor from manufacture.
So by what we're doing, we're checking all the joints, reflowing wherever we see a suspect one, and I take it that'll improve reliability for the customer.
Yes, this should eliminate the possibility of intermittent faults being caused due to bad electrical connections onto the components. We've reflowed the bad joints we found under the microscope, and we've gone back to the microscope to confirm that they are now good, and we're happy with all the solid joints. So we're now ready to assemble the power supply for final testing and then completion.
Right then, Jeff, I see we've got the power supply on
Yes.
test at the moment. Can you tell me what tests we're carrying out right now, please?
Certainly. What we're going to have to do with this is we need to check it across its load range from minimum load to maximum load, and probably just a bit over. We need to check the voltages are correct, the voltages don't change under load, that the stability is good, and then we need to check for noise levels on the output, make sure there's no ripple, no noise, or intermittent variations in output voltage.
Okay, can you just go run through the equipment we're using then to show what tests are being carried out that
Certainly.
you've just described?
We have the power supply, we have an active load. This gives us a variable load on the power supply across its working range. We have an analyzer, a virtual bench analyzer, which gives us the terminal voltage on the power supply and the AC noise on the output of the power supply.
Can you tell me then what the power supply is doing right now and show the load increasing so we know it's working to manufacturer specification?
Yes, this is a 12 amp power supply. It's a 24 volt output. We have the active load on here. The output is 24.5, you can see on the screen and on this screen. And what we're going to do, we're going to increase the load from 3 amps all the way up to 12, then to 12.5, just take it slightly into overload to make sure it can cope with that, and back down to 3. So we're going to take it in 1 amp steps. And what I'm looking for is a very large change in output voltage, which will be correct. Take it to say 13 amps, back down to 12, and we'll leave it there for a little while to make sure the power supply performs accordingly while I take some measurements. So I'm looking at the terminal voltage, I'm looking at the noise level here, I'm at 100 millivolts per division, And you can see the noise is really no greater than 20 millivolts peak to peak, and that's within manufacturer specifications.
So at this point, are we happy then the repair's been carried out successfully, the power supply is working to specification and will be reliable for the customer?
Yes.
Would you mind giving the viewers a quick summary of the repair we've carried out for this power supply, please?
Certainly. When it came in, we assessed it, and on the assessment we found that the pulse transformer had failed on a hybrid tile. That was the major fault. We replaced that, and then we carried out what we call a standard overhaul procedure. A standard overhaul procedure is to replace components that can cause a fault in the future to improve reliability. That was replacing the electric capacitors, any opto-isolators, power resistors that were burnt, checking all the solder joints to IPC standards, thoroughly cleaning the board on the unit to make sure that it can cool correctly, checking the thermal contact of the power devices, and then finally reassembling and giving a full test.
Thank you. Hi Lisa, I see you have the repair power supply in front of you. Can you tell me what you're doing now, please?
This is the final stage before dispatch, where we check the item, making sure it's ready for the customer. All the procedures have been followed, the repair documentation has been completed, and the item's got its Fletcher Moorland tracking number on it.
You've now seen some of the processes and procedures that we go through in repairing power supplies here at Fletcher Moorland. I hope you've enjoyed that, and I'd just like to say thanks to Jeff and Lisa for the input you've put in there. And if there's any other equipment you'd like to see videos of how we do, then after the presentation, please ask. Thank you.